Welcome to the 15th session. So we're now going to continue with theory. And what we can say is that so let's give a definition on the kernels that will essentially allow us to have an implicit choice of the feature map. So definition, oh, it's not good. So definition 15. So a asymmetric. Okay, so now I chose lowercase, which is not promising in my case. So a symmetric function k that goes from the sample space times the sample space to the real line. So this is called a positive definite kernel. Okay. On the sample space if the matrix that is that comprises these guys, and this is ij from 1 to some m, is positive semi-definite, this is for all x1 up to xm and m in the natural numbers. So in the notes, I have chosen the natural number symbol to represent all of them without 0. And so I will be explicit adding 0 when needed, which is essentially never. Okay. Okay, so this is the definition of a positive definite kernel. And so let's now give a theorem that some of you may have seen in modern statistical methods. So if k is a k is a positive definite kernel, then there exists a Hilbert space. Okay, so I won't go into details of what a Hilbert space is, although I hope most, if not all of you knows. So essentially you should think of it as a generalization of a Euclidean space that could even have infinite dimensions. That's really all that we need in terms of intuition. We're not going to use the structure of a Hilbert space, but you should know that it has an inner product. Okay, it's a vector space that has an inner product, and so of course because well, and we're going to use this inner product, so that's all we need from the structure of a Hilbert space for this course, of course. There exists a Hilbert space, calligraphic H, and the map. I mean, this is in the notes now. Yeah, it should be in there. Such that this K can be actually written as the product or the inner product of these two guys, where precisely this inner product is the one I was talking about. So does someone want to ask something? Okay. Where this is the inner product of calligraphic aids. Yeah. Okay. So that would be the first part of the theorem, which is telling us precisely what we were wondering. So can we choose the kernel, and then will this automatically give us a feature map? And the answer is positive if we choose a positive definite kernel, right? It may be that we have no idea what the phi is, by the way, at least as an existence result. Yeah. I mean, in many cases, you know, in the common kernels, we know. Anyway, so then the second part tells us, you know, something more, because we would be generally worried about, you know, how to choose the kernel, or how to optimize, how to get the parameters that we need to fit the model. So then this is telling us that we can, you know, if we wish to find the best feature map, you know, through choosing this kernel, then actually reduces to a finite dimensional problem, which is something that is great, yeah, in practice. Okay, so furthermore, if this guy is real, by which I mean that elements in it are going to be mappings, from, you know, from the sample space to the real line. That's what I mean. And we have L to be, so L, capital L, is going to be a loss function that is going to go from the labels to, well, this applies more generally than just classification, but anyway, from the white space to times the real line, and the real line comes precisely from capital H being real, and then this goes to the positive real line. So if this is a loss function, and we take lambda greater than or equal to 0, then we have that, you know, if we try to write the expression that we generally try to optimize, is this guy here. So we generally assume independence, so we can separate each of them. And then note that now we're writing the image of the covariates through some H that is in the Hilbert space. And then we take this, which in the cases that we've been seeing would correspond to the rich, you know, penalization term, so the L2 term. So, you know, if we wish to find, or if we wish to minimize this over all of the elements in the Hilbert space, right? So we wish to find the best feature map, then it turns out that this is the same as minimizing over Rn, the quantity given by this here. Okay, where this capital K we see there, so this guy here and this guy here, sorry, it didn't fit very well. This capital K is simply the matrix with the xi's, xj's for x, for I and j going from 1 to n, okay, rather than m. So this is just the data, so the covariates from the data. Okay, so that's the statement of the theorem. So let's now move on to, I'll leave it there for you to see for a sec, but in the meantime, let me get the R, let me get R ready. So if you have any questions also, feel free to ask. Sharing's paused. Okay, so let me stop sharing. Okay, so you should be seeing now the R Studio. And the practical. So this I will basically upload a new version as we finish because it's done now. Okay, so take a look at the solution. So someone sent me an email. I'm sorry I missed it until this morning, so I couldn't react to it to try to post the solutions a bit earlier. Yeah, I'll try that so that you can take a look at the solutions beforehand. So I hope everyone has taken a look at this, because then it explains, this alternative view of the optimization problem from SVM. And I think someone is unmuted, by the way, because I can hear some noises.
Could I quickly ask about what you just wrote down?
You mean on the iPad?
Yeah, sorry, I was a little bit slow with that. I kind of wanted to read your notes to see. Like maybe this is really obvious to everyone. What is the L doing? Why is it from like y cross r to r plus? And so
that's a loss function, right? So you just try to measure the distance between your label, say, if we're in a classification problem, and the and then so okay, so I guess so think of a linear model. In the linear model, the y is not the label, but rather just the response, right?
Yeah.
And then h there could be the linear predictor. And so you're trying to measure the distance between the response and the linear predictor.
Yeah.
Right? And so that makes sense, I hope.
Yeah.
So an example? Okay. And then in other cases, what we have, in GLMs, for instance, it would be the same idea, but now rather than being the difference between them two, it's just a different, you could take the deviance. So that depends on this G, but G, you choose it. So it's part of the capital L, basically. So I just didn't want to, so the general way of writing that is the way I wrote it, so that you can encompass a lot of models in it.
Okay. And so if we're in a classification sense, I should think of the L kind of comprising of some sort of implicit classification from HXI into the space Y, perhaps.
Yeah, so you should think of L as embedding in it the, some structure of the algorithm, yes.
Okay, and the two L's are just different formulations of the same thing in the two different setups?
Yeah.
Okay.
Yeah, and so they should be the same capital L's, right? They should be the same.
Well, they've got different arguments, don't they? Oh.
Yeah, they do, but not, right? As in, they take values in the real line anyway, so the arguments.
Sorry, so is that a ki dot beta dot b?
Exactly, yeah. So that's so you fix the ith row, and then you're multiplying the
I misread, thought it was a comma. That makes a lot more sense.
Right. Good. And so there is a comment also in the notes about that. So at the end of a paragraph, so just take a look at that, see if that clarifies it a bit. As in, well, it's not really much more than what we're saying, but it's just to say that the optimal H is then given by the linear combination of these guys. No problem. And just to say, for instance, as an example in classification, you could be taking the log likelihood, yeah, for instance, in the logistic classification, for instance. So we introduce that as a function. Okay, so maybe you want to take the negative log likelihood, but anyway, that's yeah. Okay. Yeah, so I hope everyone took a look at this alternative way of writing the SVM optimization problem, because it explains this cost argument in the SVM function, And it's just, it's just the usual game of Lagrange multipliers again, or of the same similar flavor. Do you have any questions about that alternative?
I have a question, if that's all right.
Yeah.
It was in the minimization line as opposed to one of the maximization lines. You said that beta 2 squared by 2 is more computationally friendly.
Yeah.
Could you explain why, please?
Well, yeah, maybe that was a bit of an. Well, no, it's fine. Yeah, I thought it was an overstatement, but in any case, yeah, I mean, it's just simply because when you differentiate the L2 norm of a vector, you will get square roots, and then it will be annoying in many ways. While if you have the square, then you're literally just differentiating squares. So differentiating a square gives you a linear function, and actually with the divided by 2 term, it goes away as well. The 2 that would come down in the derivative. Does that make sense?
Yeah, thank you.
Okay, yeah. So that's very common. That's a totally common thing to do in stats. Sometimes you would think, well, maybe I'd rather have the L1 norm of things, but you make a compromise and take the L2 and then square it, because then you can, in many occasions, that gives you closed form solutions and this kind of things.
For the minimization problem, are we minimizing over the slack variables as well? Because it doesn't say.
Yeah. So I sort of ignored that. But yes, the slack variables, you sort of, they should move in some sense. Yes.
Because you can write out what they actually are, right? If you're trying to minimize over them, it's just the positive part of 1 minus yi beta naught plus xi transpose beta, right? You just take, if that's greater than 0, you pick that. If not, you pick 0. I'm just wondering why because I mean, most the other formulation of this I've seen in modern statistical methods didn't have these slack variables. It just kind of had the positive part of 1 minus.
Yeah. So these are different ways of seeing things. But somehow I feel for the practical bit, it's nice to see these slack variables. They give you intuition, I feel. From a more analytic point of view, then I agree with you that the other formulation, is just something you plug into the computer, yes, and the computer will understand better.
Okay, thank you.
Yeah, sure.
With the same optimization problem, is it the case that observations within the margin, so with non-negative slack variables, is it the case that the inequality will be an equality for those observations?
Yes, and let me also say that slacks are not going to be negative, so they can only be 0 at most, right?
Okay, thanks.
Yeah, sure. So, yeah, so I mean, let me just for a sec think. Yes, I mean, the answer to that is yes, if you look at the first optimization problem, so the one up here, if you look at the last one, then what is the definition of a margin, right? Is a bit elusive. So it would be actually, you would have to look at the size that have the lowest value and then work it out from there. But then implicitly that will, or automatically that will tell you that every one that is within the margins is actually having psi greater than 0 and an equality here rather than an inequality. So the answer is yes, but it's a bit harder to argue it in this one.
So did you say you'd uploaded the file with solutions?
I hope so. Should be here.
Thanks. I was just in the wrong place.
Yeah, should be there, and also on my website if you find that faster.
I want to know. You said in the practicals that the argument cost is used to specify the regularization or cost of parameter C, which is in one-to-one correspondence with N. And I want to know why it's one-to-one correspondence.
Yeah, so this is the same as with rates and lasso. I mean, what we're doing here is using this alternative view coming from Lagrange multipliers. And, you know, I mean, I cannot give you an expression that tells you exactly how this bijection goes, but it is the case that if you minimize this problem, then there will always be an n for a given C. There will always be an n that you can that will give you the same solution, or and the other way around. And so what you could do is to look at a simpler optimization problem, and there you will be able to work out the relationship between the two. But in general, you just cannot find bijection that goes from one to the other. But just think about it intuitively, right? I mean, certainly as the n goes to 0, what you're doing is you're not allowing this sum to be greater than this n, so it will be very small, so the size will be very small. And here in this alternative, as C goes to infinity, you will have essentially, you're penalizing this sum a lot, and you're forcing this guy to be small. So it's not, as a hard restriction as this one is, but if you take C large enough, then you will eventually force these things to be as small as you like. Yeah. And the other way around. So if you let the capital N be very large, you will be essentially imposing no condition here. It's the same thing if you take C small enough, right? If you take C small enough, then you will essentially be, this term will be vanishing from this sum, and your optimization problem will only be looking at this pretty much. So you have this one-to-one correspondence.
Thank you.
No problem.
In the practical notes, you say choosing a good kernel depends on the problem at hand, and it's a non-trivial task whose full analysis is beyond the scope of this course. With this full analysis, do you mean some of the stuff we did in modern statistical methods, or is there more theory behind choosing a kernel beyond using cross-validation?
When you say statistical methods, I guess you mean modern statistical.
Yeah, sorry, modern statistical.
So I don't know. I mean, I haven't taught or sat that course, but I mean, I'm aware of some of the things that are there. I don't know whether you have seen, whether you've written out this capital K in terms of a basis of a Hilbert space and looked at the regularity of the elements of that basis and such things. Have you?
Not the regularity, I don't think, but we've written it out in terms of the basis of a Hilbert space.
Well, yeah. So essentially, what you can say is that this will, So if you look at that basis, then it contains some regularity. It basically, the basis will give rise to a functional space, and then the functions in that functional space, the regularity of them will determine the regularity of the boundaries, of classification boundaries, and you could sometimes explore the regularity of the boundaries in the data space, and then try to match those things. So you could be doing things like that, which we're not going to do. Basically, that's what I meant. But essentially, I mean, I gave the three key things that you would sort of look for. So first of all, what is the intuition behind the K? Well, it can be a measure of similarity, for instance. And generally that is the case because we're using K to substitute an inner product. So if you had an inner product between X and X prime, well, you have some, I guess it represents slightly, so it doesn't necessarily, but it does represent, or it can represent, if you like, the K measure of similarity, and actually can represent exactly the opposite. So there are some kernels that will give you exactly the opposite. And so what you take for the K will depend on the application at hand, right? At least in terms of that intuition as to whether you want it to be a similarity measure or just the opposite, whether you want to keep the fact that it has that vectors that are orthogonal will give you 0, and so on, right? I mean, it's just a bit too many things that really depend on the application at hand. So really for that, you would need to go into the application and say, okay, so what is it that I want here? And that's not something we're doing. And then another thing that is very typical is to have K, to respect certain structures of the data. And for instance, here I give rotation and translation. So you don't want, I think it's clear, right? You don't want the classification to change depending on rotation or translation in many cases, right? And these are just some. I mean, so as you can probably tell, there are a lot of things that one can say about this, and it depends on the application, basically.
Okay, I see how these points make sense, but in practice, I suppose you just get like a data set that's often very large and quite messy. So, for example, the data we consider in this practical, the letters, just by looking at the features, I don't see how it's immediately obvious how to apply these criteria, such as a kernel being a measure of similarity of the data. So in practice, would you just use some common kernels and use cross-validation? Is there ever a situation where you would?
Yes and no. So I think there is no harm in trying out the common kernels, and generally speaking, that's enough. And if you look at the papers, the majority of papers in machine learning will basically be applying these kernels. But if you were to do that and found some unsatisfactory results, then you would need to start questioning your kernel. and that's when you need to look into it. And in other occasions, it may be that you simply have some intuition as to why it shouldn't be one of these kernels. So if you have translation, for instance, may not be a transformation that you want to keep. So there may be a meaning in your covariates that, if you translate them, then it means suddenly that you're in a different, in a different subgroup of the data, and therefore maybe you don't want the classifier to give exactly the same, kernel operation to them. So say that you have different social classes and you don't want to be acting on them in the same way. So maybe two guys that are close to each other in X social class and Y social class, then maybe you don't want to have exactly the same type of treatment of them, for instance. Or let's see what else. And it's so that also relates to the measure of similarity. Or you could also explore your data, the space, the data as it comes, and see that some regions have more regularity and some regions have less regularity. If you were to think of a separation of a classification boundary, which of course you need to do looking at fixing a couple of dimensions and seeing what happens. But anyway, then if you have some regions that require more regularity and others that require less regularity, then for instance trigonometric functions are not going to be a good one, because trigonometric functions are always going to be oscillating regardless of where in the space they are. So you have to allow, for instance, for a function that would be, say, a product of an exponential and a trigonometric function, so that one end is more regular and then the other is more wiggly. So these are things that that just depend on the application, and you really need to get your hands dirty to say something.
Cool. Thank you. And one last little quick one. Is there a reason why the boundaries on the plots aren't straight lines in the practical?
Which ones are we talking about? So you're talking about
the general linear ones, I guess. Right.
This one here, page 55?
All of them, I guess, I think. So that one, but
so
probably more clear on the...
No, so this is just a problem of resolution. Yeah? So this should be a linear one, but you see there are little squares.
Oh, okay.
Yeah.
Yeah, cheers.
Yeah, it's a problem of resolution. It's not more than that.
Thanks.
No problem. In fact, depending on how stretched your your screen is, so you see these guys now are rectangles rather than squares, and if you have a rectangle, then this will break the intuition that, so I think I give it here the answer. Yes, okay, so there is a question here. Can you give an explicit description of the classification boundary based on the support vectors in this case? And I say that it is simply the perpendicular bisector of the two support vectors. Well, if you have this stretched, then you will not see that. So here you sort of see it because these are the two support vectors. And so if you draw a line and then look at the perpendicular and look at the middle point, then it sort of matches that. But if you had the screen sort of like that, then you wouldn't see that. So just, I guess, be careful with the shape of the plots. They can be misleading.
Sorry, I don't see why in general, if there's two, are you saying anytime there's two support vectors, the boundary should be the perpendicular bisector?
What's the meaning of the support vectors in this case? I mean, you're going to do, by the way, you're going to do this in the example sheet. You're going to prove it. So, but
I mean, are they just the closest points on either side for the boundary?
Yeah, exactly. So it's the same as looking at the convex hull and then looking for you know, as two. Okay, so if you have two convex holes and look at the line that is away from them by the same amount, then you will find that this is the solution and this is what's going on, right? Because what you're doing is the distance is always in a perpendicular line, right? Or in a perpendicular sense. And you see that if you, we're talking about intuition, yeah, because if we're talking about proving it, then you're going to do that in the example sheet anyway. So regarding intuition, if you take something that is not the bisector, then just think about it as you're changing the angle, right? So I think, is it clear to start with that the separating line is between the two, is in the middle point of the two?
Yeah, I guess like the example I was thinking of was if you had two classes where when you plot them, like say we have here, the two classes are, say, two parallel lines. And then the margin obviously is going to be parallel line exactly in between them. But then if you just added a point in each class anywhere between on either side of the margin, it seemed like you could make it so that the perpendicular bisector wouldn't work. I don't know if that makes sense.
I mean, it's not a bad starting point. So yes, so if you had two data sets that are, I don't think they need to be exactly falling on two parallel lines, but because if you start with that, then you can also add points above one of the lines and below one of the lines, and then that wouldn't change anything, I hope, in your head. Would it?
But then it wouldn't be. But then it wouldn't be a perpendicular bisector anymore. The margin.
No, I'm talking about points that are added away from the.
Oh, okay.
Yeah. In that case, it seems that it shouldn't change, right? At least intuitively.
Yeah, you mean like outside the two parallel lines, which are your point? Yeah.
And so now, if you add points within the margin, so one for each class, say. Then you will, you just need to think, you just need to draw the thing that is going on and try to. I see. Okay, so maybe what you're saying is that if you added two,
if I think I could add 2 points such that their perpendicular bisector doesn't even separate the classes anymore.
Okay, fine. Okay, so yeah, okay, so the rule is that if you can separate them linearly, then it will be the bisector.
But in that case, you can still separate them linearly.
Yeah, but you cannot separate. No, you cannot separate them linearly in. Oh, okay. So then, yeah. So then, what's going on is that it's if you cannot separate them linearly with a bisector between those two, then that's because they're not the only support vectors. So there will be, and this is something I can see geometrically, even though we shouldn't be having this conversation because we need to draw something, yeah. I
have it drawn, but it's hard to talk about the picture.
Oh yeah, no, I'm just talking about the rest of the students who may not be imagining what we're imagining. Okay. In any case, so what will happen is that you have more support vectors than just the two of these, and then the rule is completely different. It's no longer the bisector. So you will also see that in the example sheet. But you should think in terms of convex holes.
I guess I see what, in that situation, if you just kind of you could turn the line until now it also intersects with one of the other points, and then you'd have more support vectors. I guess that. Yeah,
not exactly intersecting, but certainly taking that into account. Yes. So what you would have now is say that you have now. So maybe the line is the one that is closest to 2 points in one of the classes, and then closest to 1 point in the other class, for instance, right?
Yeah, that makes sense.
Now you have the perpendicular bisector of the taking a point in one class and then the line between joining 2 points in the other. So it's only the case that the perpendicular bisector is the boundary classification, the classification boundary, if the the classes can be separated linearly and there are only 2 support vectors.
Yeah, that makes sense. I see now that there wouldn't just be 2.
Yeah.
I was also wondering, like, when I tried to plot the support vectors, when you plot on the SVM on the classification plot, is there some sort of offset there because the points don't plot in the right place? Like if I take the plot that comes from plotting the SVM model and try to plot extra points on it, they don't plot in the right place.
Were you talking about this plot here that I'm showing now, for instance?
Yeah, like I don't think you had the code to produce that included, but that's just from doing like plot the model and the data as the 2 arguments, right?
I mean, this is so. I'm not sure whether you're talking about this one or this one.
Yeah, sorry, the one on the right, the one that you get from plotting
the one on the right is it's just plotting what the SVM gives you, right?
But if you because I was trying to plot
to the coordinates the wrong way around, because it seems strange that on these plots we have x2 as the x-axis and x1 as the y-axis.
Yeah, but that's, I mean, how does that matter?
Yeah, that's not the problem I had, because I flipped them, and if you just have that plot and you just plot any point on it, it doesn't plot in the right place.
It's just like a problem with R.
I don't know how that plot is produced, but yeah, because I was just trying to add the support vectors to see that, and the points just plot in the complete wrong place.
I see what could be happening. I mean, first of all, I'm a bit surprised, but okay, so it could be that I don't think this is right what I'm going to say, but it could be that the R function is centering things around the origin using some sort of barycenter or whatever it is, something here. But it's true that but why I'm saying that's probably not the right answer here. I'm not saying it's not in general, because you saw this in LDA, for instance. The reason why I'm saying that's probably not right is because we're actually explicitly plotting things here and they give you this. So I'm a bit surprised by what you're saying. So you're saying that if you try to plot, say, the 0, 0, then it won't follow on 0, 0?
Yeah, like I have that. I tried to plot the class set means as well. And so I just plotted on that colored plot -2, -2, and it just doesn't go at -2, -2.
How did you try to plot it?
Just points, -2, -2.
Yeah. That's very strange. I mean, you can come to the example, to the office hour for this, and we can discuss it and see what's going on.
Okay.
Because actually the time is over. Yeah. Okay. So the time is over. So let's stop here. And so we basically got questions from, I don't think it's very hard practical. But if you still have any questions, then just come to an office hour, or if they are brief, then you can ask in the next one at the beginning. Okay. So thank you, everyone. If you have any other offline sort of questions, then feel free to ask for a couple of minutes now. Otherwise, we end it here.
Yeah, sorry, there's one more. I guess if this can't be answered quickly, I can come to the officer as well. But what exactly is like the markings on those plots in terms of like it marks the points as X or O, but it marks some points on either side that way. So I'm not sure exactly what the markings actually mean.
The margins?
The mark, like the markers for the points.
Support vector versus normal.
Yeah. Oh, I see.
Oh, is that it?
You're talking about the X's here rather than the circles.
Yeah, exactly.
Sure. Yeah.
And they're both different colors, I think. So I think the colors correspond to the labels, and the dots are not support vectors, and the crosses are support vectors.
Yeah, that's right.
But are any points that fall inside the margin, are they also support just because later on there's cases where like not all of the points marked with X are the same distance from the boundary?
Yeah. So this is the definition of the support vectors.
Okay, sorry. So if it's on the edge and inside.
No worries. I mean, I'm just pointing it out so that you have a reference to read it again. So support vectors are data points that satisfy the constraint, by which I just mean the constraint here. So the constraint with equality rather than with strict inequality. So, if you think about this, any point that has psi being strictly positive will have an equality. So it means the points within the margin will be support vectors. And then the question now is, what about points that have slack variable equal to 0? Well, in that case, you can have two situations, one in which you have equality and the other in which you have strict inequality. And the case in which you have equality is when the point is exactly the one that is farthest away from the classification boundary on the correct side. And then any other point that is away from the classification boundary by more than the margin will always have, strict inequality. So those are not support vectors. So this matches exactly what we have in mind, which is to say that the support vectors, if you have a perfectly separable case, then the support vectors are those that are, closest to the other class in some sense. And if you do not have a perfectly, linearly separable example or data set, then the support vectors are going to be those that are either away from the margin up to capital M, not for the margin, sorry, from the classification boundary up to capital M, or any others that are within the margin or wrongly classified. And the reason to include all of those vectors is because those are the vectors that will determine the classification boundary. So you should always think of support vectors as the ones determining the classification boundary.
Yeah, that makes sense. Thanks.
Yeah. So I will, if you don't mind, I will include this in the recording just because I think that's useful for everyone.